this particular GYAN program. And again, we have our guest faculty, Dr. Gerfred, with us. And today's session, first session, will be on application to biofuel. So directly, related session, especially for the students working on the biofuels. And I request all of you to listen carefully, as you will be having one examination also tomorrow. It will be a multiple choice based, examination, and grades will be given, and maybe it will be transferred to your academic bank of credit scores also. So seriously listen to the talks, whatever we are organizing, and then only you will be able to perform good in the tomorrow's quiz. So I will invite the guest faculty today, Dr. Gerfred, please. Yeah.
Okay, good morning, everybody. The question yesterday arose, what is more difficult, to get up on the hill to see a temple or to make a life cycle assessment? So what do you think? Anyway, it was a very nice excursion yesterday. And as we already mentioned, there will be some homework for today, and tomorrow we have time to discuss the group work. So I'm gonna introduce to you the group work. At least, as I've mentioned before, if you form maybe 4 groups or 5 groups, or however, you don't have to do it alone. You can do it together with your colleagues. And these are the main things you should prepare. You can do it either on a bigger piece of paper, kind of poster, and do it by hand. Or if you like, you can also do it on a computer and then try to upload it here. It's the main idea or the main purpose of this activity is that you learn to make a process chain, starting with the key resource on the top and the product or the service on the bottom, and in between the main unit processes, 4, 5, 6, not more. Like you have seen already in the lecture, and you will also see today, and see what are the key flows. The idea is that you select a product or service made from biomass. Of course, biofuel is one possibility. And then just say a few words. What is the goal and scope? For example, you want to know current technology here in India, and you're interested in greenhouse gases and primary energy. That's it. Or you want a full endpoint calculation of a future bioethanol production from corn stover, for example. Yeah? But at least brief, just answer these questions brief. But secondly, you make this process chain, with the main resource and the main steps towards the product, and then see at which stages co-products might occur. Where you might have maybe animal feed or straw or glycerin. You think if and then at least define the system boundaries, which is at least the system boundary at least is between nature. So nature is going in the system boundaries, simplified, and the product is coming out of the system boundary. Everything in between, you have these unit processes where you need to collect the data and make the LCA. Then, of course, what is the functional unit? We've heard that the functional unit is the element. On one hand, it's a product, and you just have to describe, is it 1 driven kilometer, or is it 1 megajoule of biofuel, or is it a liter of milk? So at least define very briefly what is the functional unit. And And then think about, because we've seen in LCA you always have to compare it to something else. Yeah? So at least think about what would be the product or service you want to compare it to. You can compare two different biofuels, but of course you also can compare biofuels with gasoline or diesel. Yeah? So this is at least the idea, and if you can put that all on one page, so to say, and this will tomorrow be the starting point, because you present your findings in the group, and then the other colleagues can comment or ask questions. I can give some comments, Professor Sorenda can give comments, so at least we have a little bit of interaction, yeah, and see if we all understand what your LCA is and what are your system boundaries. And then on Monday you can start to collect data already. Okay. Okay, so you don't need any LCA tools or databases, nothing. It's really to get a feeling to make such a process chain. Okay, are there any questions on the group work?
You can divide them in three groups.
Yeah, of course. Yeah.
So one group can take up say paddy straw to bioethanol. One group can take paddy straw to biogas, and one group can take up, who is working on biobutanol. Yeah, Manisha. One group can take up paddy straw to biobutanol. So starting with a one substrate, three different products.
Perfect. Yeah.
And then they can compare with the alternate uses, and definitely a reference may be gasoline, or in case of biobutanol, it may be different.
Yeah, that's tricky. Yeah.
Yeah, so at least within groups also they can share their thoughts.
Yeah.
Will it be fine?
Yeah, that's perfect. Perfect.
Yeah.
Yeah.
Okay.
So we have three groups. Very good. Mhm. Yeah. Okay. So I come to my lecture number 7. Zooming in a little bit more on the methodology of life cycle assessment and its application to biofuels. At least what we've seen, we are going to compare using biomass, and as we want to replace fossil energy, so we compare it to fossil energy, and this is again a graph showing how you do these comparisons. On the left hand side, it's the bioenergy system, always starting in nature with growing the biomass. Then you have the different processes and conversion processes. In that case, you're providing heat and electricity. And these blue arrows show more or less the flow of the biogenic carbon. Also on the right hand side, you see the same picture for the use of fossil energy. But for the fossil energy, of course, you start with the raw oil or fossil energy underground. So the carbon stored underground at least is also extracted, transported until you provide a certain service. But the carbon finally ends up in the atmosphere. Yeah, so you see here, this is at least what's ending up in the atmosphere, whereas the bioenergy in a sustainable way has the possibility that the carbon cycle is closed. We know that on the bioenergy side we have co-products and byproducts, but also on the fossil side you might have co or byproduct. Yeah? The oil refinery also makes raw material for the chemical industry, so at least also on the fossil energy side you might have byproducts. Today I want to start also a little bit highlighting land use and the carbon stock stored on land. And globally the forests There's a typing error in the heading that always happens. The role of forest, because globally forests are decreasing for several reasons, but the forests themselves are really a big storage of carbon. Yeah, because in the trees, in the soil, in the litter, a carbon is stored. And it's interesting to see that in the soil and in the living biomass, roughly the same amount of carbon is stored. So really big amount of carbon you don't see because it's more or less in the soil. And as soon as you start changing the forest, you might also release additional carbon to the atmosphere. Um, um, this is for the general forest, and a big issue is, of course, the tropical rainforests. They even have um, much more carbon stored per hectare. And one big global issue is, of course, the destruction of tropical rainforests. And if you only cut them down and use them once and then make grassland there or agricultural land, in that case, you really lose carbon. And this is a big issue, also relevant for biofuels, especially for the first generation biofuels, because in that case you might have, or you have in most of the cases, a kind of land use change divided in direct and indirect land use change. And this is a very hot issue being discussed the last decade, last 10 years or so. The idea is in your LCA, you maybe start converting a grassland where you have animals in the beginning, you convert that to cropland because you want to produce raw material for bioethanol or for biodiesel. Yeah? And by doing so, really a direct land use change is happening because before you had grassland and now you have agricultural land. And normally in grassland, you have more carbon stored than in agricultural land. Yeah? Um, so this is called the direct land use change because it's one piece of land you convert to another piece of land. But then you see you have less grassland. Yeah, so the animals have less grassland. So it might happen, or it really happens, that of course if we want to have grassland for the animals again, uh, we need to convert, at least as land is limited, convert forest to grassland. Yeah? And converting forest to grassland itself is direct land use change again. Yeah? Also changing the carbon pools. But from the viewpoint of the LCA you're looking, you call the second effect, converting forest to grassland, it's called the indirect land use change. So normally this is outside the system boundary of the life cycle assessment, yeah, in attributional LCAs, but at least you have to consider that if you want the same amount of grassland because you have the same amount of animals, this is called indirect land use change. And there's a big discussion within the LCA community how to include this indirect land use change. Normally, on a global scale, we all know that we convert mainly tropical forests to grassland and later on to 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 cropland, but it's not proven that it's only the biofuels pushing uh, this scheme to convert forest to grassland. There are many other effects. Yeah, for example, globally the population is increasing, so we need more agricultural area for food production. Is one reason. Yeah. The other reason is that we generally want to have more meat. Yeah, so globally, the meat consumption is really dramatically increasing. And if we need more meat, we need more animals, and we need more grassland. And this has at least nothing to do with biofuels. Biofuels maybe put an additional pressure, so to say, on the availability of cropland. So there is not a direct effect. It's a relatively complex indirect effect to really say how much for land use change is the responsibility of the biofuels. And And that is at least one reason why indirect land use change has been heavily discussed, and it's also reflected partly in the regulation on sustainability for biofuels in Europe. We have this regulatory framework, and of course there they really try to document or at least to avoid indirect land use change. So this is the direct land use change and indirect land use change. It's really a perspective from the LCA. Once it's called direct land use change within the system boundary or indirect land use change. I show you the same graph or the same message again because um, this if you have a starting situation number one here where you have the animals and a certain area of forest, yeah, so this is what you're considering. And in the first step, if you start to produce biofuels, you're converting a part of the grassland to agricultural land. That's why you see these green drops here. This is the area where you're going to cultivate raw material for first generation bioethanol. And you clearly see that then the grassland is less available. Yeah? And if you have still the same amount of animal and want the same amount of grassland, you go to the third picture by converting the forest into grassland. Yeah, then again, the animals have the same space as they had before the biofuel came. And this is then, at least from the point of view of the biofuel, this indirect land use change. And and the direct land use change, at least, is or might be considered in most of the LCAs, but you only do the land use change once. Yeah, you do it, and if you continue growing biofuel crops on this piece of land, you only convert it once. So the effect of losing carbon in this transportation is only happening once. Yeah? And then if you continue making sustainable agriculture there, at least you keep the carbon storage on the cropland at a certain level and maintain it at the same level. Only before on grassland it was higher. Yeah? So you only change it once in the overall system for the first system you build up. And the big question is, how do you distribute this initial loss of carbon over the long following lifetime or production phases of the biofuel? So it's a kind of investment, so to say, in terms of carbon investment or carbon emissions only happening once. And to be honest, LCA does not have a very simple answer on that issue. Yeah, you can say I'm ignoring it because it's only one effect. But if I produce really over a very long time much biofuel per liter of biofuel, it's very small. And the good thing in LCA is you can always say I'm not considering it. Yeah, because the most important thing in LCA is a transparent documentation. Yeah, and if you say I'm aware of land use change, but due to the reason of this and this, I excluded this in my analysis. Yeah, and if you write that there, you're totally fine. Yeah. So the most important thing, like in most of the scientific documentations, you just have to write what you do or what you exclude, what are the framework conditions. And, and in most of the studies, this direct land use change is not considered. Even the indirect land use change, which is even more difficult, because the indirect land use change can only be addressed in an economic global model, at least, where you have the population growth, the meat consumption growth, the growth of other agricultural products, the growth of raw materials for biofuels. Everything is in there, and which is a at least far away from the pure LCA. But still, it's for you. It's important to be aware that this effect is existing, and it might or might not be relevant for your LCA. But this is a quite relevant issue about land and land use change. I'm just to give you some orders of magnitude. Um, how much carbon or CO2 is stored or how much carbon you lose. For example, if you convert Greenland to sugarcane, you roughly lose per hectare 2.5 ton of CO2. Yeah, because the difference is from Greenland to soybeans, it's roughly 3 tons of CO2 per hectare. It's only happening once when you convert it. It's extremely high if you convert a tropical forest to a palm oil plantage. Yeah? This is roughly 30 tons, yeah, per hectare. You're really losing carbon because in tropical forest you have so much um, carbon stored. And if you put that directly to the amount of biofuel that can be produced in the first year on this, if you say I put all this burden on the biofuel produced in the first year, you end up with figures 370, 800 grams CO2 equivalent per kilowatt hour. So this is really a very high value. The gasoline and diesel has 250. Yeah, so it's even higher than gasoline or diesel because these carbon effects are very, very, very strong to be to be relevant in total, but it's an effect only happening once, and after the first year, of course, this disappears because then you don't have any further change in the carbon storage if you do a sustainable agriculture there. And and in Europe, in this renewable energy directive, which gives you the LCA for the biofuels on the European market, they also put some ILUC factors more or less per consensus. And they found out that for bioethanol, due to the growing conditions and the countries where it grows, this indirect land use change is significantly lower compared to biodiesel, because biodiesel is more happening in areas where tropical forests are, and therefore has a stronger effect. And there are many publications on land use change and direct land use change, and some of these publications really show that under worse conditions, the different biofuels don't save greenhouse gases at all because of these effects of land use and land use change. So it's really needs the proper framework conditions to make raw materials for biofuels. But this land use change effect, this is on this slide here. They are mainly caused or discussed in connection with the first generation biofuels, yeah, where we use this rapeseed oil, soybean oil, grains, corn, grain, wheat. So at least these so-called food crops, yeah, because they are at least addressed by land use change. As soon as you come to advanced biofuel, yeah, and this is also a key driver for going to new feedstocks, yeah, lignocellulosic feedstocks, because their land use change is not an issue at all. Yeah, so this is at least one key driver to include land use change in this consideration, because this is a clear and big advantage for second generation biofuel. These effects can be calculated. Yeah, so there are some programs available. I've shown you one. I will later in the afternoon go a little bit more into this program. I've chosen this BioGrace program because it's relatively simple to be operated by somebody who is not so involved in that. It's an Excel-based calculation system, and it's relatively transparent and gives you many default data already. Yeah? So you find many data, robust and good documented data, with which you can start to calculate land use change effects. And so we will see in the afternoon there are many other tools, but this is at least a very good one. It's a little bit outdated because it's not valid for for the current regulation in Europe, but anyway, it calculates properly, and you can always insert your own data. Yeah? But the really good thing is that the calculation is very transparent, very clear, and it gives you many default values that give you an order of magnitudes. For example, if you want to calculate the land use change effects. And in the afternoon, I will show you with this program, you can also do the overall calculation on biofuels because all the key elements are there with the necessary input data. And you can use the existing data in there, or you can override it with your own data. And I'll show you this in the afternoon. I also show you in the afternoon another model. It's from America, the GREED model. They also have in that model, I also will show it in the afternoon, they also have one specific part in the tool dedicated to land use and land use change. So at least this is a very good way if you're further interested, or if this is somehow relevant in your education, to work on land use change. These are two programs where you get a very good insight on the orders of magnitudes and the data that are relevant to calculate land use and land use change. So this thematics of land use and land use change is at least very closely connected to the production of biomass, because we've already seen yesterday that it's always a question what's happening on that piece of land if you do not produce bioenergy, which we call the reference use of the land or the biomass. And so these two questions are quite relevant. What happens on an arable land if no energy crops are produced for your purpose? And there are different possibilities that have somehow to be included. And you will see it later on if I show you more process chains. This reference use of the land is relevant, but also of the biomass. The reference use of the biomass is mainly relevant if you use residues like straw, use cooking oil, manure. You always have to think what's happening if I do not make an energy carrier, if I just keep the current usage of it. For example, we discussed yesterday the combustion or the burning of straw in the fields happening around here. Yeah? If you use the straw for something else, you avoid this, and this gives you an additional benefit, of course, of the production of an energy carrier out of straw. Yeah? So this is it's quite relevant, and you will see it in the coming pictures again that this is included. I show you the same picture a second time. I already showed it to you yesterday, but I think it's good to repeat because this is really an essential graph to see if you want an energy service from bioenergy or fossil energy. These are the key processes: collection of residues, cultivation of biomass if you're in agriculture, the transport, the processing to bioenergy carrier, distribution of the bioenergy carrier, and the use of the bioenergy carrier. And the fossil system, at the first glance, is at least this more or less the same processes, also transportation, conversion, use, and distribution. But for the biomass, we've seen we have these co-products, and these co-products somehow must be assessed in the overall system boundary. And in most of the cases, you look what is the conventional way to produce this co-product, and if you can avoid that, you can subtract it from the emission of your bioenergy, which we call also the substitution approach, which is one way. Secondly, the reference use of the residues and the area. Yeah, so if what's happening on this piece of land if I do not produce grains, for example, for bioethanol, or what's happening with the residues, with the straw, if I do not make bioethanol, for example. So this is quite relevant. The system becomes really tricky if this reference use also provides you some product, because then you also need on the bioenergy system an idea how you can further provide this product that was provided before by this reference use. So it's really a complicated thing. And these elements you see here, the collection of residues, cultivation of biomass, the reference use, these are the key elements that are relevant for the land use change, directly and indirectly. I've mentioned before. So this is the generic picture that always works. And if you zoom in now for specific applications, yeah, if you say I want, for example, produce electricity from wood chips in a power plant, and I compare it, for example, to a coal power plant, the picture looks more or less like this. On the right hand side you have the coal extraction and the thermal power plant from coal providing electricity, and on the left hand side you're collecting the wood chips, you transport the residues, you process it to wood chips because they need to be cutted or dried, you burn them, and then via the electricity grid you can provide electricity to the consumer. In that case, the electricity grid is included here because here the functional unit is really a certain amount of electricity at the user side. So at the socket on the wall, for example, I want 1 kilowatt hour already on the socket of the wall. Therefore, you have to include the electricity grid. If you define your functional unit just at the gate of the power plant, which is also okay, then you don't have to consider the grid. So this really depends on how you define your functional unit. And for example, if we use sawmill residues for this power plant, the question is what happened to them before you start using them. In that case, it was an Australian case study. On one hand, it's natural oxidation taking place because if a pile of wood, sooner or later it disappears and all the carbon is re-emitted in the atmosphere without energy use, and that has to be considered. It's the same if you take out forest residues directly from the forest. You also change in the carbon storage in the forest because you take out the wood, which otherwise would have lay down on the ground and disappear slowly and release CO2 slowly. If you take it out, you also change the carbon stored in the forest. Yeah? Therefore, this reference use is also relevant considering the carbon storage. But this is at least the picture how it looks like if you make electricity. A more complex one is biodiesel from rapeseed. Compare it with fossil diesel. Still, it's the similar picture again. Yeah, you have here the cultivation of rape, the transport, the proceeding of the rape to rape oil first, and from rape oil to biodiesel, distribution of biodiesel. Here we have a biodiesel bus, and you compare it with a conventional diesel bus. But then we have the glycerin as a byproduct. The reference case is you can make synthetic glycerin out of natural gas. This is the biggest commercial way because we have a quite high demand on glycerin, and that can be made also from natural gas. But if you make it from biodiesel, of course, you avoid the emissions of making glycerin from natural gas. Yeah. Secondly, the animal feed. Yeah, it's an animal feed. It avoids the cultivation of another animal feed. In that case, we've taken the cultivation avoided from soy feed production, which is quite relevant for the Austrian and European situation because we are importing very much soy feed, mainly from Southern America, to Europe. But if we make our own biodiesel, we really make our own animal feed, and we really substituting or avoiding the import of soy feed oil. So we are avoiding emissions that might occur in South America if we now make our own animal feed. Yeah. So this is very close to reality to really see what's going to happen, and this reference use of the area. In the past, in Europe, we had an overproduction in agriculture. Yeah? Therefore, the farmers got money doing nothing on the field, yeah, to keep the make it a set aside land. Yeah? because then the prices kept at a certain level. Otherwise, they would decrease too much. So the farmers really got money doing nothing on their field, yeah. Which is from the point of LCA the best way, because that's the easiest way to include the land use, the reference land use, if it's a set aside land. So at this time, this was also a key driver on the beginning to introduce biofuels, because there was agricultural land left. But this situation now really changed. We don't have now it's the other way around. We are still lacking on agricultural land due to several reasons, but the economics was a little bit different in the past. Yeah. So you see again, this is for biodiesel, and in all these graphs, it's very important that in these eclipse you need an equilibrium, so you get the same amount and quality from the left-hand side system and the same amount and quality from the right-hand system. Yeah, the same amount of animal feed with the same nutrition content, and the same amount of glycerin with the same quality, with the same pureness, and transportation service, of course, a certain distance, the same, and of course also on the area, the same amount of area being used on both sides. So this is a way to control if your system boundary and setting up of the system is really in line, and for the calculation you need the same on both sides to have an equilibrium. Yeah, that's the way you can read it. In some cases, we have seen that for the co-product you can also apply, for example, energy allocation. Yeah, that would simplify that picture a little bit, because then you don't need these reference uses of the glycerin and the animal feed on the right hand side, because you just subtract, or you just give the energy weighted part of the emissions for the biodiesel on the left hand side. That makes the LCA a little bit simpler, so to say, which is also okay. Yeah? So you can always apply energy allocation also to this product. Just specify and write it down. I applied energy allocation using these heating values, give you a share of 50 to 60 or whatever, which is then allocated to my bioenergy carrier. I have two more examples. One simple example is the next one. It's a comparison of a wood chip boiler to a reference system with an oil boiler. In Austria, we had many oil heating systems in the past, and we put much effort to really substitute raw oil heating, because we're a cold country, so we need a heating in winter. Nowadays, really, oil heating systems are forbidden in Austria. So you're not allowed to build a new house and put in an oil heating system. Yeah. Now we are going also to forbid natural gas for heating, because it's fossil based, and it's so easy to build a house which needs less energy first and then power it with biomass or power it with a heat pump, which is much more sustainable. So in the past we made many comparisons showing that the heating with wood chips is much more environmental friendly than heating with oil. And this is just one example, again, using forest residues. As we have so many forests, we have many forest residues which otherwise would be left in the forest. Yeah. So there was no use for the branches and the top, so they have been left in the forest. But if you also take them out, you have a good fuel, a renewable fuel, to supply renewable heat to houses or communities. And the last one is just the most complex one, I would say, because so bioenergy itself is already relatively complex in terms of LCA, and the biogas and the biomethane within bioenergy is even one of the most complex ones. And so I'm happy that one took the biogas for the work also for tomorrow. But maybe this is not so complicated because you have only one feedstock. Normally for biogas you use different feedstocks, yeah, and the more feedstocks you use, the more difficult it became. In that case, we use corn or maize as a starting point, which was also or is still common in Europe, because from 1 ton of maize you can really make much biogas. But on the other side, corn is a food or feed, so the same debate with like for bioethanol, and we comparing electricity and heat. We compared that to electricity coming from the natural gas power plant, and the rest is a heating system using oil. So in that system, we use first cultivation of maize. So the question is, what is the reference use of this piece of land? It's in that case set aside land. Then additionally, we had also substituted cultivation of maize as an animal feed. Yeah, and if we do that, we are lacking of animal feed. Yeah, because if we now use the corn for biogas, so we have the animal feed again, and to replace this animal feed, we're going back to the cultivation or the import of soy feed. So now the soy feed appears on the other side of the bioenergy system, because we are using the maize not for food and feed, we're using the maize for biomethane, but we still have to make sure to provide the same amount of, animal feed. Then we also put grass in. We also put grass in the biogas facility, in the biogas plant. Yeah, the grass before was just composted. So there was at least just a composting, but the composting gives you a fertilizer. If you compost, you also do that in organic farming. If you compost something, all the nutrients are there and you can reuse them. So the composting gives you a fertilizer. The good thing is that also the digested material coming out of the biogas plant also is containing fertilizer. Yeah? So on the first glance, you also get a fertilizer. You not get it directly from the composting of grass, you get it a little bit indirected from the biogas plant. So this is very important that the fertilizer balance is kept. And then we have also put in manure, yeah, in the biogas plant, which is very good because manure contains much water, and then you have enough water in your biogas system that the anaerobic process is working quite well. If you don't digest the manure, you just store the manure, and again the manure has a fertilizing component. Yeah, you bring in the fertilizer. This is not lost. If you put it in the biogas plant, you get the same amount of fertilizer, more or less, out of the biogas plant. So at least the fertilizer balance is quite the same. If it's a little bit different, you have to add here on one side also the production of maybe of mineral fertilizer. Yeah? And you see here, this already looks relatively complex because of the different feedstock, and each of these feedstock has a reference use, and this reference use also provides you a product. It could be animal feed, it could be a fertilizer, and that really has to be reflected again in the overall picture of the LCA. And again, in these red eclipses, there's an equilibrium of the quality and amount of fertilizer, of grass animal feed area you get from one side. It also must be the same on the other side. Yeah, so again, you can check in your calculation that it's the same on both sides. When you store manure and not digest it, the manure, also in the manure, they're starting an anaerobic process when you just store it. Yeah? And you release relatively big amounts of methane from the manure storage. Yeah? And in that case, for example, if you avoid the storage of undigested manure, you also avoid these uncontrolled methane emissions, which gives you also a big environmental benefit. So digesting manure in a biogas plant is a very good thing to reduce greenhouse gases. And this I will will touch on the next slides that in agriculture, methane emissions and nitrogen oxide emissions are very strong emissions coming directly from agriculture. So they are also reflected here in the LCA. So if there's a possibility, like here for avoiding the storage of undigested manure, it's a good way, and you count that in this box of storaging manure, you have a negative, finally a negative methane emission, because you really are able to avoid these methane emissions. So I'm telling you a little bit now also about the greenhouse gas emissions that occur directly in agriculture, because that is also relevant to understand in the LCA. So the agriculture is having on one hand CO2 emissions from soil preparation. You might have, they have methane emissions from the animal housing, or for the animal housing the animals, and you have these N2O emissions, which are relatively relevant on a global scale, but also on national scale. The N2O emissions are mainly dominated by the agricultural sector, yeah? Because these N2O emissions from fertilizing in agriculture really are a strong contribution to the overall N2O emissions. And globally, it's nearly 90% or even more directly coming from agriculture. It's similar with the methane emissions. Also, the methane emissions to a high share, also more than 80% or 85% directly coming from agriculture. Yeah, that is part of agriculture. That's why I want to show you this a little bit more in detail. And you see here, these are the nitrogen sources globally in or it's in Europe. I'm not sure if it's in Europe or if it's globally, but you see that the agricultural soil management has a substantial contribution to N2O emission, because in agriculture you need nitrogen that things are growing. That's a very important fertilizer. But as soon as you put nitrogen on a field, and it does not matter if the nitrogen is coming from manure or from grass, or if it's minerally based nitrogen, you always have an effect that a part of this nitrogen is directly converted on the field to N2O emissions. And this is at least the pity behind that. The process I've shown you here is very complicated. Yeah? The process of this N2O formation in agricultural soil, that's a big thing. So I even don't understand all the details. For me, it's only relevant to know how much N2O finally is going directly to the atmosphere. Yeah? And what we in Austria, for example, on a hectare of land in agriculture, you have per year 2 to 5 kilogram N2O emissions per hectare. 2 to 5 kilogram. You don't see them, you don't hear them, you don't smell them, but on the agricultural area, depending on the season and everything, but at least on the end of the year, between 2 and 5 kilograms of N2O is directly emitted on this piece of land. And the CO2 equivalent factor of N2O, I don't know if you remember, it's 300 times stronger than CO2. Yeah, so if you emit 1 kilogram of N2O, it's equal emitting 300 kilograms of CO2. So if you have 2 to 5 kilograms N2O per hectare, and you put that on the CO2 equivalent level, it's 600 to 1500 kilograms CO2 per hectare and year, the emissions from agriculture. And this is really a strong part, and we will see later on in the biofuel assessment that these N2O emissions show up also in the final results. And therefore it's so important to know, to understand the effect, and also to quantify that when you do the inventory analysis. And in most of the cases there is a relation between the nitrogen input to the field and the N2O emission output. It's a relatively good estimation, so many formulas calculate this based on the nitrogen you put in. But the overall complex system is very complex. It depends on the water content, if it's raining or not raining, and many, many things. But the N2O emission finally is a very relevant source. And here you see some examples for the N2O emissions, and also to really avoid these emissions is very difficult. Yeah, so because it's a process taking place anyway. Yeah, it's even all the food we consume, they all have. So if you make a balance of a salad or a vegetarian lunch, yeah, it's all grown in agriculture. Even all these products roughly have half the greenhouse gas emissions in life cycle assessment from this N2O emission in agriculture. Yeah, you cannot really avoid them. And if you once use or need an N2O emission factor, the International Panel on Climate Change is providing a good database for all the national inventories. Yeah, and this is always a good starting point. You find many emission factors in this IPCC reporting, very easy to find. You find them for oil, gas, N2O, coal mining, or whatever. So this is a good initial source, because these factors are also used for the national inventories. And there you find, for example, for sure an average N2O emission for the agriculture in India, which might not be valid maybe for the field outside, but still it's a good national average. If you know more about the fields you are considering, of course you can further modify it. If you don't have that, it's best just use the average Indian value you will find in the greenhouse gas balance of your country, which is at least a relatively reliable and meaningful value. And secondly, agriculture is also much responsible for methane emission. Yeah? And methane emissions from, this is the overall balance, at least methane emissions in agriculture depend on the animals, to say it simple, especially cows. They're producing much methane. Yeah? You know, they have to re-eat. I don't know the English word, but they always uh, they have to, their digestion needs much eating, and they have to beat it again and again, and they're producing much methane on both sides of the cow. Methane is coming out, and then also in the manure management you have this uncontrolled um, methane formation, because it's a wet stuff, and in that wet stuff you have anaerobic areas where methane is emitted. And here you see that roughly 3/4, 75% come from the animal itself. It also comes from other animals, but cows are quite the most dominating one. But in the manure, you also have much methane emissions. And this is good to be here, because you're all vegetarian, yeah? Because the vegetarian really avoid all these emissions. And these emissions occur, of course, with all the meat, but unfortunately with all the meat, with all the animal products like milk or yogurt or so on. So in the balance of milk, yeah, you find very much methane coming from the cow, yeah, in the overall LCA. Yeah. So still this methane you find in all animal-based products, and they are also very much dominating the overall greenhouse gas, balance. Secondly, so beside what's happening in the cow, yeah, from the different feedstocks you see here, so the cow is most dominating. It's not the chicken and not the pigs. It's mainly the cow for milk and for meat, having 60% or 65% of the global emission really come from the cow. And secondly, methane is also emitted in rice cultivation. Yeah? Because rice is growing in water, and in that water you also have anaerobic processes, and therefore also the rice production. That's because it grows in water. You cannot change it, so to say. So also the rice production and the rice has certain methane emissions. I never made an LCA on rice, so I cannot say how much 1 kilogram of rice is having on greenhouse gases. I have no clue. That would be once interesting just to get an idea how much it is compared to potatoes or grains. Yeah, I don't know, but we know of course that it's an anaerobic zone where you have these methane emissions. And this is even a more detailed picture, but it summarizes at least relatively well here for the N2O and the methane emissions, where in the different activities, agricultural activities, you have this methane in the N2O emissions. You also have methane emissions when you bring, for example, manure, if it's digested or not. Anyway, if you bring the manure on the field as a fertilizer, you also have on the field methane emissions still, and N2O emissions. So you see they are happening on different places in agriculture, and the processes behind are relatively complex because it's all natural based, and it really depends on the framework conditions. But still, the emission factors provided by the International Panel on Climate Change, these emissions factor at least give you a good estimate for the different emissions in the different areas in agriculture. Okay, so this is my final slide for the morning session, the take-home message. You see here again this picture, we call it at our institute the left and right picture. Yeah. So in LCA at our institute, we always, when we start doing an LCA, we ask, did you do already the left and right picture? This means exactly like this. You have one system on the left-hand side providing the same services as a system on the right-hand side. And the right-hand side at least describes the reference system. It might use fossil energy, might also use other energy carrier. But in that case, you need the same energy service on the bottom from both sides. You have to consider the reference use of the area and the reference use of the residues, like used cooking oil or straw, and of course the co-products of bioenergy. I hope I could explain you the understanding of land use change, indirect land use change, and direct land use change, that these are relevant effects that can be included in LCA but must not always be included, and only the direct land use effects are really part of LCA, where indirect effects are even much more complicated and not directly part of LCA. We've also seen that considering the biogenic carbon pools and cycle, where you store carbon in soil, in plants, in litter, is relevant in the LCA as soon as you start changing these pools. And finally, we learned about the N2O emissions and the methane emissions associated with agricultural practices, that they are happening, and at least showing you where in agriculture these emissions occur. So I'm ready for this morning session, and I'm still here to answer any questions. Thank you very much for listening. So everything was clear?